All right, welcome back to the deep dive. Today we're taking on something uh, pretty fundamental to computer graphics, but something that can be incredibly complex to get right, especially in real time. We're talking transparency.
Yeah, transparency, huh?
Yeah, we see it everywhere in the real world.
Mhm.
A hazy, smoky room, the way light bends through a glass of water, even just the subtle translucence of a leaf. Getting a computer to recreate these effects convincingly and do it quickly enough for interactive applications, that's a whole other story.
It really is. And it goes way beyond, just making things a little see-through, right? I mean, we're trying to simulate how light interacts with these surfaces that only partially block it, like how much gets through, how it changes direction, refraction, all that. Then you have stuff like fog or smoke
Hmm.
that also affects how we see things.
Yeah. So like with the smoke example, the more smoke there is between us and an object, the less of that object we can actually see, right?
Right. And that's where things get really tricky for computers. See, in traditional rendering, when you're drawing a solid object, the complexity is more or less tied to the number of pixels you have to fill on the screen, right?
Hmm.
But with transparency, a single pixel on your screen can be influenced by tons of things layered behind it. All those overlapping transparent bits contribute to the final color. So suddenly the complexity isn't really about the screen size anymore. It's about the depth and the arrangement of all these transparent elements in 3D space.
Gotcha. So if we wanted to go all out, like absolute top-tier realism for complex transparency, no matter the cost,
Yeah.
what would be the go-to method?
Oh, hands down, that would be path tracing.
Hmm.
Path tracing is like, the holy grail of rendering. It's where you simulate individual light particles as they bounce around the scene, hitting surfaces, reflecting, refracting, the whole 9 yards. That's how they get those crazy photorealistic visuals you see in movies, where every little detail, every little reflection is just perfect.
Yeah.
But there's a catch, right? To do that properly, to simulate all those light paths, you're talking about a crazy amount of calculations, especially with transparent objects.
Huh.
Light can go through multiple layers, bounce around inside. It just explodes in complexity way too much for real time, even with today's hardware.
Can you give us an idea of just how many calculations we're talking?
Sure. Think about like a simple wine bottle. For a single ray of light to travel from your eye through the air, the glass, the wine inside, then back out, you're looking at least 5 interactions with different surfaces, right?
Yeah.
And that's just one ray for one pixel.
Yeah.
Then you have reflections, shadows, all that. Suddenly you're talking about 15, 20, maybe more rays per pixel, easy.
Wow.
And now multiply that by like the millions of pixels on your screen, 60 frames per second, and yeah, you see the problem, right? It's just an insane amount of computation.
Yeah. Yeah. And there's also the issue of noise, right? That kind of grainy look you sometimes see in renders. How does transparency make that worse?
Oh, yeah, good point. So that noise you're talking about, it comes from not having enough samples, not tracing enough light paths to get a smooth, accurate representation of the light distribution. With solid objects, you can often get away with fewer samples and then clean up the image with denoising algorithms. But with transparent materials, it gets really messy.
Update.
The noise is kind of spread out at different depths within the object, so those denoising tricks don't work as well. And another thing, the usual method of using information from previous frames to smooth things out, that doesn't work reliably either because the transparency can change so much between frames.
Got it. So path tracing, while amazing, is just too much for now. Which brings us to this concept of a visibility function. What's that all about?
Ah, yes. So the visibility function, you can think of it like a way to describe how much light makes it through a certain distance from your viewpoint through the scene, right? So it maps the distance to how much light is actually transmitted, the transmittance. So
Mhm.
like if you're looking through a hazy cloud, that visibility function would kind of gradually decrease the further you go into the cloud.
Right, right. Makes sense.
Now, if it's a sheet of glass, it would stay at full visibility until you hit the glass, then suddenly drop, and then stay at that lower level for everything behind it.
Mm-hmm.
So basically, the visibility function captures how much light is blocked or transmitted along a line of sight.
Okay, so thinking about it, a totally solid, opaque object would have a really simple visibility function then, right? Like it's either all the light or none of it.
Exactly. Opaque rendering, it's just a special case of this visibility function, just a binary on or off.
Makes sense.
This idea, it's not entirely new. It actually stems from techniques like deep shadow maps,
Yeah.
which were originally used for figuring out how much light gets blocked for shadows. But now it's been kind of broadened to handle all sorts of visibility problems, including transparency.
So we've got this idea of the visibility function. Now, this paper focuses a lot on what's called order-independent transparency, or OIT. Why is it so important that the order of things doesn't matter when dealing with transparency?
Okay, so imagine you're looking at a stack of like semi-transparent colored gels, right?
Hmm.
If you just blend them in whatever order they happen to be processed, the final color you get could be totally wrong.
Yeah.
Traditional rendering, it often has to sort all these transparent surfaces front to back for every single pixel on the screen.
Right.
And that sorting, it's super expensive, especially in complex scenes. Plus, it doesn't work well with the way GPUs like to process things, in parallel.
Yeah, because that sorting creates a bottleneck, right? It prevents things from happening all at the same time.
Exactly. So order-independent transparency, it's all about figuring out ways to deal with transparency without needing to know the exact depth order of everything.
Okay.
This way, you don't have to sort. You can use a fixed amount of memory per pixel and the rendering timescales more predictably.
Hmm. Makes it much more efficient for real-time stuff.
Absolutely.
So if they're not sorting, how do these OIT methods actually represent this visibility function? The paper mentions a bunch of different techniques.
Yeah, they use a whole bunch of clever tricks. Some try to achieve accuracy through clever layering, like depth peeling, which essentially does implicit sorting. Others use probability, like stochastic binary visibility, randomly checking depths to get a good estimate.
Right.
You've also got methods that store a set number of transparency samples at different depths, like occupancy maps or K-buffers. And then there are the more mathematically heavy approaches, like Fourier opacity maps, which use wave-like functions to represent opacity, or weighted blended OIT, which works by making certain assumptions about how opacity builds up.
Right.
Then there's moment transparency, which uses statistics, like summaries of the transparency along array. And finally, there's the method we're focusing on today, wavelet transparency, which introduces a whole new way of representing this visibility function.
Wow, a whole zoo of techniques. And the paper also mentions that refraction, that bending of light, adds another layer of complexity that these OIT methods don't handle directly. Why is that?
Yeah, so the OIT methods we've been discussing, they mostly deal with how much light is blocked, right? The intensity.
Right.
Refraction, though, is about the direction of light. When light goes from one medium to another, like air to glass, it bends.
Mm.
And to simulate that accurately, you need a whole different set of mathematical tools.
Mm.
Plus, refraction brings its own set of visual effects, most notably chromatic aberration.
Ah, yes. The paper had that really cool image of the glass ball with those colored fringes around the edges.
Yeah.
What causes that?
So chromatic aberration happens because the refractive index, that is how much the light bends, it's not exactly the same for all colors.
Oh, interesting.
Think of a prism splitting white light into a rainbow. It's kind of like that. When light goes through something curved and transparent, like a lens or that glass ball, the different colors bend at slightly different angles. And that creates those colored fringes, especially at sharp edges where you have a bright area next to a dark area.
Right, right.
That picture of the glass ball, it's a great example of how that looks in the real world.
Mm-hmm. So in something like path tracing, where you're already simulating the paths of individual wavelengths of light, chromatic aberration would just happen naturally, right?
Exactly. Because you're already taking into account the different refractive indices for each wavelength, the chromatic aberration just pops out as a natural consequence of the simulation. But for real-time rendering, simulating all those wavelengths, it's way too costly.
Yeah.
So in games and other real-time stuff, they often approximate it with post-processing effects, kind of faking the chromatic aberration you'd get with a real camera lens.
Okay, that makes sense. And this leads us to phenomenological transparency. Can you break down what that's all about?
So phenomenological transparency, it's a philosophy in real-time rendering, right? And it basically says, look, instead of obsessing over perfect physical accuracy for everything, let's focus on getting the visual appearance right, the things our eyes are most sensitive to. So it's about creating a unified solution for all the different aspects of transparency, but doing it in a way that's fast enough for real time. It combines techniques like WBOIT and colored stochastic shadow maps with approximations for refraction, diffusion, ambient occlusion, shadows, all that. It's all about perceptual fidelity over strict physical correctness.
Okay. So today's deep dive is about research that builds on this phenomenological transparency framework. Like, what's new? What are they bringing to the table?
Exactly. This paper introduces two main things. First, a new way to represent the visibility function using wavelets. And second, a new simplified but effective way to approximate that chromatic aberration we were just talking about. The goal here is to match or even beat the quality and performance of the current best method, which they consider to be moment transparency, but potentially with a simpler implementation.
All right, wavelets, we've heard that term before, and image compression and stuff. How do they fit into representing transparency?
Wavelets, they're a really powerful tool for analyzing functions or signals at different scales, big picture and fine details and at different positions. Think of it like this. Fourier analysis breaks things down into global frequencies.
Hmm.
Wavelets are different. They're localized, meaning they have a limited range in both frequency and, in our case, space. And that localization makes them really good at representing things like the visibility function, which can have both sharp changes like the edge of a glass and smoother variations like the density of fog.
Okay, so how does this actually play out when you're rendering transparency? The paper talks about three main steps.
Right. The first step is all about building an approximation of the visibility function using these wavelet coefficients. They do that in two passes over all the transparent geometry in the scene, or at least the bounding boxes that enclose them. Then the second step is another pass, but this time they actually shade the objects, calculate their colors and all that. But this shading is weighted by the visibility function they just approximated.
Right.
And finally, they combine those shaded transparent results with the opaque parts of the scene that were rendered separately. This is where they also apply other effects like that new refraction approximation, diffusion, all that.
Hmm. And the paper outlines four specific steps within that overall three-step process.
Exactly. First, they figure out the depth bounds for each pixel that might have transparent stuff in front of it. Second, they use that depth info to build a wavelet coefficient buffer, which is the heart of their visibility representation. Then, they accumulate the color and properties of the transparent objects, but weighted by the visibility from those wavelet coefficients. And finally, they combine all that with the opaque background and apply those other cool phenomenological transparency effects.
Okay. Now, storing these wavelet coefficients, it sounds like it could take up a lot of memory. How do they keep that under control?
So for wavelets of a certain rank, they store a fixed number of coefficients per color channel. And they pack those coefficients really efficiently into a fixed amount of memory, often 32 bits per channel, sometimes even sharing an exponent to get more dynamic range. For instance, using rank 3 wavelets, which means 7 coefficients per channel, you end up with 48 coefficients total, needing 64 bytes per pixel.
Okay, so it's a fixed cost per pixel.
Right. And the idea is that even though it's a fixed amount of data, this wavelet representation can capture the essence of the visibility function better than storing lots of individual depth samples.
Got it. The paper mentions a radiance compositing equation and then talks about switching to a net absorbance function.
Right.
Why change how they're representing the transparency?
Okay, so the radiance compositing equation, it describes how the light from all these different transparent surfaces combines to create the final pixel color, and the visibility function comes into play there.
Right.
The problem is when light goes through multiple semi-transparent layers, the amount that gets through tends to decrease exponentially.
Mm-hmm.
So working directly with those transmittance values, it can lead to all sorts of precision issues when you're doing calculations. So they switch to absorbance, which is basically the negative logarithm of the transmittance. Now, this might sound complicated, but what it does is it turns multiplication into addition. Instead of multiplying transmittance values for each layer, you add up the absorbance. And adding is much more stable and easier for computers to handle, especially with lots of layers.
That makes sense.
It's
Like if you keep multiplying small numbers together, you can lose a lot of precision really quickly.
exactly.
And they specifically mentioned that for things like glass, which they call discrete interfaces, this absorbance function is basically a series of step functions, right?
Absolutely. At each surface, like when you go from air to glass, the amount of light absorbed jumps up suddenly. And for this, they point out that hair wavelets, which are the simplest type of wavelet, essentially little step functions themselves, are a really natural fit.
So they're using these step functions to approximate the step-like changes in absorbance.
Precisely.
Okay, so how do they actually use these hair wavelets to build up this approximation of the absorbance function?
They combine a scaling function, which captures the average absorbance, with a series of wavelet functions at different scales and positions. These wavelets handle the finer details, the sudden changes, and the specific values they use for these, the coefficients, they get those through integration by parts. What's interesting is that the wavelet coefficients are always negative, which means they decrease the absorbance, and the scaling function coefficient is always positive, representing that base level. And those coefficients, they directly relate to how opaque each layer is and where it's located in depth.
Got it. And they mentioned this approach is pretty efficient when it comes to updating the representation if the scene changes.
Right.
Right.
Yes. Because wavelets are localized, when something changes, you only need to update a small number of wavelet coefficients.
Okay.
And that's really good for dynamic scenes where things are moving around because you don't have to recalculate everything all the time.
Makes sense. They also make a specific choice about how they represent depth. They use linear depth. Why that choice?
Yeah. So the way you represent depth, whether it's linear with distance or not, can affect how well the wavelet approximation works. Using linear depth means that the scales of your wavelet basis functions are uniform across the depth range.
Mhm.
There are other ways, like screen space depth, which are nonlinear, and they might be better suited for other wavelet bases. But for this work, they stuck with linear depth for simplicity.
Okay. And they do something to address those blocky artifacts that you sometimes get with simple hair wavelets, right? They use linear interpolation.
Exactly. If you just use the hair wavelets directly, you can get a stair-stepping effect, which doesn't look very smooth. So to smooth things out, they do linear interpolation between the points defined by the wavelet bases.
Mm-hmm. Okay. And finally, for the technical details, they mentioned using render output variables or ROVs or atomic operations to update those wavelet coefficients efficiently.
Right.
Those.
Okay, so when you've got all these transparent fragments contributing to the same pixel, you need a way to update those shared wavelet coefficients safely, especially on a GPU where things are happening in parallel. RVs and atomic operations, they're hardware mechanisms that let multiple parts of the program write to the same memory location without messing things up.
Right.
And they say that if the graphics hardware supports floating point atomic operations, it's a pretty straightforward implementation.
Mm-hmm.
Otherwise, you can use something called compare and swap, which is a little less efficient but still gets the job done.
Okay, so that covers the wavelet transparency algorithm.
Mm-hmm.
Now, what about their new way of approximating chromatic aberration? How is that different from what phenomenological transparency was already doing?
So, phenomenological transparency already had a way to approximate refraction, the bending of light. They'd calculate a refraction offset vector during the shading pass, telling them how much to displace the background image. This new chromatic aberration approximation, it adds two things. First, during shading, if the material has a refractive index greater than 1, like most glass and water, they cube the transmission coefficient.
Qubit?
Yeah, it's kind of a hack, but it's a way to simulate the absorption of light within the material, making the back surfaces darker, more realistic.
Oh, interesting.
It also affects internal reflections, making them slightly dimmer than external ones.
Like how the reflection of a lamp is a bit dimmer on the inside of a glass ball compared to the outside.
Exactly. And the second thing they do is during compositing, instead of taking just one sample from the background, they take 5. These samples are spread out along a line in the direction of the refraction vector, and the distance between them depends on how strong the refraction is.
So they're basically sampling a little line instead of just one point.
Right. And for each of those samples, they use a specific weighting function that adjusts the contribution of red, blue, and green based on the sample's position.
Oh.
This is meant to mimic how different wavelengths of light bend by slightly different amounts.
Okay, so it's a way to recreate those colored fringes.
Exactly. And their weighting function uses smooth mathematical functions to blend the color contributions so it looks more natural, more like the real thing.
All right, let's jump into the results. Figure 2 in the paper visualizes the visibility function for different scenes. What did they find there?
Figure 2, it's really interesting. It compares the approximated visibility functions from moment transparency and their new wavelet transparency to the ideal or ground truth visibility. They tested 3 scenarios, a car in fog, a wine bottle, and some smoke and fire. And what stood out was that in the fog, wavelet transparency seemed much better at capturing both the gradual decrease in visibility and the sharper changes at, say, the car's windshield.
Oh.
With the wine bottle, both methods kind of smoothed over the sharp boundaries between air, glass, and wine, but moment was a slightly better fit at the very first interface. And then with the smoke and fire, wavelets seemed to be more accurate overall, better at capturing those quick changes in visibility.
Right. And then they had figure 3, which showed how different OIT methods actually performed in rendering different scenes.
Yeah, figure 3 is where the rubber hits the road. They compared MLab, WBOIT, moment transparency, their wavelet transparency, and they used a high-quality A buffer as reference.
Mm-hmm.
In simple cases, like a sphere of particles, moment and wavelet were both pretty close to the A buffer, much better than MLab or WBOIT.
Okay.
But the real test was that bistro scene with all those glasses. MLab ran into problems because it has a limited buffer size. WBOIT had trouble with the depth ordering, producing weird results. Moment was better, but it over-smoothed the highlights and made the glasses behind the first layer too dark. Wavelet, though, it was almost indistinguishable from the A buffer in that scene.
Oh, wow.
Probably because those hair wavelets are really good at capturing those sharp transitions at the glass surfaces.
Right, and what about the scenes with alpha masking, like the leaves?
With the leaves, the focus was on how they handled the transparency at the edges. MLAB underestimated the coverage. WBOIT and Moment had some noise or discontinuities. Wavelet was the closest to the smooth transitions of the A buffer.
Mm-hmm.
So overall, from Figure 3, they concluded that wavelet transparency was the most robust, consistently performing well across all the different types of scenes.
Okay, so visually, wavelet transparency seems like a winner.
Hmm.
What about their new chromatic aberration
Yeah.
approximation? They showed that off in Figure 5, right?
Yes, Figure 5 was all about the chromatic aberration. They showed the scene rendered without refraction, then with the old refraction from phenomenological transparency, and then with their new 5-sample method.
Hmm.
And the difference was clearest at the edges of the glass, where the new method created much more convincing colored fringes like the ones in that picture of the glass ball.
Right.
And they argued that even though it's not a perfect physical simulation, it looks much more realistic.
Okay, and they also showed a frosted glass globe, right? Figure 6.
Yeah. The frosted glass globe was to show off the refraction, diffusion, and the new chromatic aberration all working together. They even compared it to a path-traced render, noting that the slight differences in the refraction pattern were likely due to their holosphere model versus the solid one in the path-traced reference.
Mm-hmm. And finally, for performance, how did wavelet transparency stack up? They had that table, Table 1, with the timing for the bistro scene.
Right, Table 1. It showed the time taken for visibility and shading for different methods. And wavelet transparency was actually very competitive, right in there with moment transparency.
Mm-hmm.
So the improvements in quality don't seem to come at a huge cost in performance.
All right, let's move on to the discussion. They talk about some advantages of wavelets for this compared to other techniques like Fourier opacity maps. What were those?
The big one is bandwidth efficiency. Wavelets are localized, so you only need to look at a small number of them to represent a given part of the visibility function. Methods like Fourier opacity maps often have to access all their coefficients all the time, so as things get more complex, wavelets are more efficient. They also explain why they chose the simplest hair wavelets for this.
Hmm.
Higher order wavelets might be better in theory, but hair wavelets are simpler and faster.
Right. They also talk about the numerical robustness of their method. What's that about?
Numerical robustness basically means the calculations are less likely to have weird errors. With their wavelet approach, the coefficients are always calculated by adding values of the same sign, and that makes the whole thing more stable compared to methods where the values can fluctuate more wildly.
Got it. They do point out some limitations, though. One is the lack of shift invariance in the wavelets they used. What's that mean, and how could they improve it?
Shift invariance basically means if you shift the input signal, like the depth of the transparent objects, the output representation should also just shift without changing its shape. The wavelets they used aren't perfectly shift invariant. So if the camera moves slightly, the visibility approximation might change in ways that aren't just a simple shift. They suggest looking at complex wavelets, which are almost shift invariant.
Okay.
But those are harder to optimize for real time. Another option is stationary wavelets, which are truly shift invariant but need way more coefficients.
Mm-hmm. Mm-hmm. And they also mentioned the need for 2 passes over the geometry, which is something they share with other methods. They had an idea for how to get that down to 1 pass, right?
Yeah, they want to see if they can calculate those wavelet coefficients in the same pass where they shade the objects. The challenge is that you need those coefficients to figure out the visibility for shading in the first place.
Right.
So they're thinking about using the coefficients from the previous frame and projecting them to the current view. But they admit that handling occlusion, when opaque objects block the transparent ones, is a tricky problem they haven't solved yet.
Okay. And finally, they reiterate some of the visual benefits, like that reduction in rigging artifacts they showed in Figure 4. What's the take-home message about the strengths of their method?
They basically say that wavelet transparency looks as good as or better than the current best method, moment transparency. And it often does it more efficiently, using less bandwidth, especially when there are lots of opaque surfaces. It's also really good at handling those sharp transitions and transparency and avoiding those weird ringing artifacts. Overall, they think it's a strong contender for real-time transparency, balancing quality, speed, and ease of implementation.
Well, this has been a great deep dive into transparency and this new wavelet-based approach. So to wrap things up, what are the biggest takeaways, the key benefits of wavelet transparency?
I'd say the main benefits are the improved representation of the visibility function, their clever new way to approximate chromatic aberration, and the fact that it works well across a wide range of transparency challenges. It's visually impressive, often better than the existing state-of-the-art, often more efficient, and potentially easier to implement.
It's amazing to see the progress being made in real-time graphics. It feels like we're getting closer and closer to that point where you can't tell the difference between real-time and pre-rendered stuff.
I know, right? And this kind of research, it really makes you think about what the future holds. I mean, with the way GPUs are getting faster and the algorithms are getting smarter, who knows what we'll be able to render in real time in a few years.
It's exciting to think about.
Yeah. I mean, imagine real-time graphics that are just as good as like those super high quality offline renders.
Hmm.
It could open up some incredible possibilities for interactive experiences, things we haven't even thought of yet.
Definitely something to ponder.
Uh,
Well, thanks so much for taking us through this research. It's been really enlightening.
My pleasure.
And to everyone listening, thanks for joining us for another deep dive. We'll catch you next time with another fascinating topic.